So first of all, yeah, is it using this? First of all, you can either use Meluxina, so the cluster, or you can use the collab. Doesn't matter which one you use, it's just personal preferences. This is more interactive, and the other one has some scripts, some submission scripts, and so on. But they have the same content, so maybe I'll give you a couple of seconds to scan them. And let me know if it works. Anyone managed to open it? Yeah? And now I will show you how to get the script on Meluxina. So if you want to have the folder maybe up, I will show the QR code again. So here I log into Meluxina in the home directory. So in case anyone wants to follow along, when you log in, you're in your home directory. For me, there's a bunch of stuff, but for you, most likely it's empty. And then you can see in history. There's an extra allocation for us. Is this big enough? Can you all read it? So in this project here, you have it's the same one as yesterday, and here you have my name, and in there you have scripts, and you can just copy them to your home directory. And then you can look into the folder, and there's some Python scripts, some Markdown files, and some Bash scripts. And the Python scripts just contain the same information as the notebook, and the Markdown also has the same information. Just all the text and so on. And then you have the submission scripts that you can use later, which you just have to submit. All the necessary info there. So it's just allocating some partition and then running the scripts. So later you can run them by doing sbatch. Okay. Okay. So I will tell you which script you can run, but you can just explore it, and they're enumerated, and there's not many of them, so I think you will manage. Has anyone encountered any issues yet? Yes, please. You can just stay there and then copy. Yeah, you can just copy the whole folder and then should be fine. Famous last words. Okay. I personally will just go along with the notebook. I will explain a bit the different lines of code, and you can just follow along executing the cells. You can play around with the settings and so on, but this is really just to give you an overview.
Im Chat wird nochmal nach den Notebooks gefragt.
Okay.
Kannst du den Link nochmal in den Chat packen?
Ja.
Du siehst, Maxim, das wäre eigentlich fast besser. Wenn du den Chat sehen könntest. Kannst du ihn vielleicht noch bei dir aufmachen?
Warte mal kurz. Step by Step. Das ist eher der Link hier. Ja, oder du sag mir einfach, wenn irgendwas im Chat ist.
Okay, dann muss ich halt auch die
Ach so.
lassen. Und Sound ist, also, aber ja, ich würde gerne den Screen gedreht. Das geht ja nicht, aber gut, wenn das nicht.
Ich gucke manchmal in den Chats rein. Maybe someone, if you see something in the chat, let me know. I will try to look at it once in a while. But
unfortunately, we cannot turn the screen.
Okay. Are we back?
Yeah.
Okay. So. Okay. So we will just study like a little toy system throughout the day. So it's just the alanine dipeptide. And we will use JAX-md first to run a normal MD, get you accustomed to it, and already give you some scripts that you can use in your projects too. And then we will look at the dihedral angles of this peptide, and then show that with standard MD we can't sample the potential energy surface or the free energy surface of these dihedrals properly. And then we will go to metadynamics for that. So in the first cell, in the notebook, you have one cell that installs the environment. So you would first you have to connect to some partition, and then you can run the first cell here to install the environment. And once that is done, there will be some cryptic messages. Just ignore that, then you can run the next cell. So I will do it in parallel. So now it's collecting the environment. Then we are importing a bunch of stuff. So of course JAX-md, and then also some stuff from the Solar repository, which is some helper function to let us use it in JAX-md, and the potential itself. So first, the first thing is, of course, we need to have the starting structure, which is just the string here in XYZ format that we provided. So you can just run that, and then you can see it loaded the structure just as usual with ASE. And then you have the formula and the different atoms, which are important because we have to define the dihedrals later. You can, yes, I didn't import it. Well, anyways. Okay, so somehow it's not loaded the 3D view, but now you can look at the structure, but we will also have a image later on. I will just show that. So this is the structure, and we will look at the two dihedral angles, phi and psi, and look at which angles are sampled from the MD. Okay. So before we dive into how to run this exactly, I will talk a bit about JAX because not many people are familiar with this. And JAX is a machine learning package, which has all the stuff you need to create machine learning models. It also has very powerful just-in-time compilation, which I will also talk about, and nice gradient functions that lets you define gradients of functions very easily or higher order derivatives, which will not be topic here, but it's just in general good to know. So JAX-md uses a paradigm that's called functional programming. Maybe some people here are more familiar with PyTorch, where you create objects, and these objects can then be changed, or you have some inheritance of other objects that are layers above it. Here, we don't really use that. We use functions for everything. And key points here are that functions in JAX have to be pure, which means there's no side effects. So the function gets some input and will always return the same output. There's no logic that decides some other some other effect is triggered, like a print statement or some if statement and so on. It will always just return the same output, and this is really useful for JAX because this lets it cache these functions, compile them, and then execute them very fast. Yes. Yeah.
It's not really. You have to copy the environment to the project.
It's strange because Sergio tried it out, but
I think he has access. But
I gave everyone access. Let's see.
Then maybe it's just a secret message. Maybe okay.
And because I gave access to everything, the environment too.
No, but if you look on your script, there is a command load. Yeah, maybe it's not.
Oh, really?
Maybe it's mistaken. In the stage.
Ah, this one. Okay. Ah, fuck. Oh, okay. Has to be. No, wait. Oh, yeah, right. That's true. Okay. Yeah, there's one thing we just noticed. So when you are on Melexina, there's a mistake in the submission scripts, and we only noticed it now because a colleague tried it, but he had access.
Working on the Meluxina, or are you using?
Is anyone using Meluxina? Okay. I will change the scripts, So the important thing is here, I gave the wrong project directory.
You can also do it in the background.
Yeah, maybe you can change that. It's just this line. Okay. So Florian will change it, and once you're done, you let me know, and then you can copy it again. But let's just continue. So okay, so the functions are pure, and then we also have immutable arrays. So that means that you can't just take an array and do something like this, where you say, okay, in the first position, I want to have this variable x. What it does in NumPy, for example, it would change that in place, but this is not possible in JAX. So you have certain functions that we see later, like the neighbor list update, that always return you a new list or new array, and nothing is changed in place. So, which is important because you can't do something like this, where you just call update and expect this to be an object that will be updated. You will always have to reassign a variable. And then something very important is also, especially if you're coming from ASE, in ASE you have the dynamics object, for example, and when you call .step, it will update the dynamics object, so the step will update or the energies and so on. This is not the case here. Here you will call the step function and it will return you some new state. So you can't just update a state or something or expect anything to change within that state. And then finally, there's many wrappers in JAX, like JAX-JIT, which I will talk about in a second. JAX.grad, which gives you the gradient or the derivative of any function. And then JAX.vmap, which gives you a batched version or a vectorized version of your function, which is very helpful too. So you can write any function and then use JAX-vmap, and then you have a vectorized function. And these are placed around the function. For example, here we have the energy function, which we will see later, which gets transformed into the force function, and then it's jitted again, and which returns another function. So we are working a lot with functions, and functions are on the same level as any other variable. Yeah, and if you stack them, you get, in the end, the final transform function. And this is not something unique to Solar. It's just how JAX works, and then JAX-md. And maybe you are asking yourself why we bother with all of this, because this puts some constraints on how we write our programs. But this really is geared towards using this just-in-time compilation. So if you know, for example, C++ or Fortran or something, which first you have to compile your code, and then you can use the final executable for running your code. Here it's similar. You write your code, and then you run it, and before the first execution, JAX compiles the code. So this is what happens when you first call it, and maybe you will notice it later. The first iteration will be very slow, and then subsequent ones will be very fast. So that's what it says here. And what happens, it goes through the whole function, your whole code, just with shapes and data types, so nothing value dependent, and trace the whole program and then compile it using XLA, which is just the language in which it's compiled in, and then to the machine code. And this is important because you have to write your program with everything in mind, only for the shapes and data types. So you can't use any values here, for example, or some commands like an if statement on the values. And this, and also important, this when the function gets compiled, everything that is not part of the pure function, like a print statement, only gets printed during the compilation, which is not very useful. So if you write a code, there's ways to let it print, but you have to keep that in mind too. And just to make it a bit shorter, because this may be a bit dry, but we have to use static values, like when you do a for loop, at compile time it knows that then n cycles, but as I said, you can't do something like if statement that is based on a value, like if this is larger than 5, do this. This can't be done because it would only trace it once and then only use the value it used during tracing. But I mean, you can read through this more content. So here, use this project from this folder, but it should be.
Because there is. There is
this one. Yeah.
I see.
Yeah. Okay, and the reason why this is even a thing is that this just-in-time compilation at the end gives you a compiled code, and it's optimized for, especially for GPUs and TPUs, and this makes everything very fast. You saw in the talk today that for Socrates, for example, they used some algorithm tricks to make it faster, but now we also use JAX, and especially stuff like matrix multiplication and so on, and batched multiplications are drastically accelerated. Okay. Does anyone have a question until now? Okay. If you couldn't follow along, but you have a question later, you can just ask me. But now let's get into JAX-md itself. So I think we ran this, yeah. So now we have some settings because we want to run some optimizations and some dynamics. So first of all, of course, we have to define the data type. Now we're in a gas phase, so we just take a very long cutoff. And these things are coming back to JAX because we will later run. Do you have a question? Okay. We will run a loop you will see later. And first we have to allocate some memory, but I will explain you more about this when we come to there. So we have to define some buffer for the neighbor list. And this is now how you define the energy and force function of solar using JAX-md. So first we have some, we have to define that this is done in a vacuum. And here we use this helper function from solar, where we have to define the potential, which we import from solar. We have some way of computing the displacements because we're in a vacuum. This doesn't really matter. It's just the normal distances. We have to define some species, and again, these multipliers, which I'll explain in a second. So this, if you run this, you get 3 objects, 3 functions. It's the neighbor list for the short range part, which is for the neural network part. And then for the long range part, for the long range potentials in solar. And then you get an energy function. It will just produce the energy if you put in some geometry. But we also, of course, want to have forces. And in JAX-md, there's a helper function that you pass the energy function, and then it will create the force function. And what it does is just here in this commented code, it's just called grad, jax.grad, on the energy function with respect to the positions. And this is how you define gradients of functions in JAX in general. And here you already have this helper function from JAX-md. And yes. Is the gradient computed numerically? No, it's automatic differentiation. Yeah. And it can go to arbitrary orders of the derivatives. And it can also produce Jacobians and so on. And yeah, so it's a bit easier to use than in Torch. And then we also did our functions. So this is, again, in the first iteration, we launched this. It will compile the whole model and everything around it.
Just too stupid.
So you go to script, then you go to
I mean those I find, of course. This is not the problem, but the path is not.
But it's just this. This. No.
But don't you need like a conf setup script?
I should just use a Colab. I'm sorry,
yeah,
but
then let's just fall back to polar. It's fine.
Yeah. I could fix it, but I can't do it. I can fix it in the break if the people want to use it, but I can't do it right now.
Yeah, I can otherwise install one in there.
But you just have to, because you can also whatever. Okay, now we have to run this, and then you see we create the neighbors using our neighbor functions, and then we have the positions and the box, and it will give you the neighbor list. And the energy function then takes the positions and the neighbor list and the box and just create you the energy. And should have something like this. Now we want to relax the structure, so we can do optimization with JAX-md2. So first we are using fire, which you may know from ASE as well. Just some thresholds, a number of inner and outer cycles, which I will show you in a second. We have to define that. And here we have the code for doing optimization. So if you want to use JAX-md in your project, you can basically take this code. So we have the fire algorithm from JAX-md, and here we give it an energy function, the shift, which we got from here from the where we define this as in vacuum. And then we can also JIT the apply function, which is the one that actually performs the optimization. So we can have a completely compiled optimization function too. And then we use the init function that we got to have a first initial state, again with the positions and so on. And then we define a step function. Okay, just as a head up, like this is very detailed, but later I'll show you how to do it with the Solar package, where we wrapped all of this complexity, and you can just run it with a simple command line interface. So in the step function, this just describes what happens at each iteration. So it has some state that you have as an input, like the initial state we created here, which contains the optimizer state and the neighbor lists. And then we use our apply function that we got on this state, this initial state, for example, and get another state. So this is what I told you. It doesn't change the object itself. It just gives you another object. And then we have a new positions, of course, because we just did an optimizer step. So we have to compute the neighbor lists again. And then we can take this whole function and then also wrap it in the with the JIT wrapper here, and so the whole function is compiled. And now we can actually run the optimization loop. So we have our number of cycles here, and so there's two loops happening here. So one is completely coded in Python, which is the first one here, and then we use this to have a compiled loop inside of JAX. So instead of doing this lengthy Python loop, it will compile the whole loop, and which makes this part very fast. And it will just create a compiled version and only return something to Python if it's done. And we just use here the energy and force function to monitor the optimization. So you can run that too, and you can of course play a bit with the settings if you want. And maybe you notice that the first one will be a bit slow, and the other ones will be quite quick. My laptop doesn't have a GPU, but especially on GPUs, you can see the difference. Yes, please. Yes.
You have Python, then you have this JAX.
Mm-hmm.
So you have a loop within the loop, or is the JAX just a smart implementation of your Python loop?
It's basically a loop in a loop. We do this because this loop here is completely compiled and you can't access anything from there. So when it runs the number of steps in the compiled code, and I can't intervene with Python in there. We will see later in the MD example where this can be relevant. But for example, here I just want to print out the energy and forces and see how the optimization is going, but I can't access this from this loop. Yeah, does it make sense to you? Yeah. So here, it takes this function that we defined before and just calls this fire steps per cycle times, and creates these states and so on. So, yes.
Following up on the same question, or maybe a little bit different. I see that you're calling the function that you decorated through line 3-4.
Mhm.
That function only takes 2 arguments, and you're providing 3.
Yes. So here, this here is the state of this. It's this one is in brackets, so it's a tuple. The state is just a tuple of these 3 variables.
Oh, okay.
Yeah. Okay. But it's good because this is just the state here. So in this JAX for loop, it will just update these variables and put them in the function all the time. Yeah. And here the 0 is just we started 0 index. And the nice thing is here you can also use the JAX.vmap to, for example, do like a batched optimization. But we will also see this in the afternoon session. Okay. Now we actually go to the molecular dynamics, where we want to sample these dihedral angles. For this, we have to define the atom indices, that correspond to these atoms in the peptide. And then we have to set up some things for the integrators. So like the time step, we have to change the units a bit, just like in ASE. Now we define the temperature, so at 300 Kelvin, and then some arguments for the Nose-Hoover chain thermostat. So these are just a bunch of settings. And then we define just a helper function to get the dihedral angles. And now again, we have the same syntax basically as in the optimization case, where we have we set up the integrator, which just gives us back a initialize and an apply function. And here we give them all the arguments it needs, and also the energy function. So then we have the function that creates the initial state and the actual integration step. So we also JIT them. Then we create a new the initial state. And then again, just like with the optimizer, we create a step function. Now it is just called carry, but could also be called state. And use the apply function, so the actual integration step on the state, and update the neighbor lists again. And now we can actually run the dynamics. Here, we first define how many steps we do, and again, this inner and outer loop that we used also in the optimizer. And this is now the cell where we actually run the dynamics. There's a bunch of, we print a bunch of information like the energy, the temperature, and so on. But the important part is here. Again, we have this outer loop and this inner loop, and this means that, again, all these integration steps are done with the compiled version, which makes it very fast. We do this JAX block until ready because we want to measure the time, and this just stops the whole function until it's really compiled and also ported to the device, for example, if you run it on GPU. It's just a detail if you want to do some timings. And one thing that is important now is this. Here we check if the neighbor lists overflow, because as I said, this all happens in the compiled version, and the number of neighbors is of course dynamic, depending on how close the atoms are. It can be that there are more neighbors suddenly, which would mean that maybe the array is larger now. The number of neighbors is larger, so the array is larger, but we use fixed shapes, and this could cause JAX to start compiling again. And each time JAX wants to compile something, it takes time again, and we don't want our dynamics to constantly compile the code, which is why we give these buffers. So we allocate more memory that we actually need. And here we just check if this buffer is large enough. Yeah, sure.
Then, if it's not large enough, that's not automatically reset buffer.
So I will show you later in the command line interface that this is already automatic in Solr. So if you use the CLI, it will automatically use it. Otherwise, you have to write these lines. Yeah. Okay, and then we can run it. And first, it will take some time because it compiles everything. So, but then it starts running. So in the end, it compiles everything from the model to the integrator, everything in one compiled code, and then we'll run the dynamics. And then you can see here how it's evolving. And this will take a bit, again, because it's just on the CPU, but also because the molecule really benefit from, parallelizing all the operations. Yes.
Yeah, evaluate questions. So because you have fixed shapes, does that mean that if you want to, for example, evaluate a data set that has molecules with different amounts of atoms, that also you can just use the same compiled version?
Kind of. So for example, if you would look in the code of Solr, and because it's a graph neural network, this would be a problem, right? If because then, as you said, then maybe you train on a molecule data set that has small molecules and large molecules. And the way you solve this is, again, you check before you train, for example, or even evaluate, you check the sizes, and then use a bigger array that covers all of them. Right?
Yeah, I think it's PySAGES, they have like this giant tensors or something, and I think it's something similar. Make n fill it to zeros or something.
Exactly. So they're just padded.
Yeah.
And then you have like ghost nodes that don't contribute to the actual result, but are only there to have fixed shapes. Yeah. So there usually, there are some values in there that are just made up. So it's just that it's stable. But later on, it uses a mask to know which parts of the array are actually atoms and which parts are just trash. So in the end, for example, if you have this aggregation of different node features or node energies, it will only take those that are real, and the rest will just be thrown away. So you can't, which also means that it does the computations too, right, for these nodes, which are useless. So you can't just say, okay, I'll make a huge array, so I will cover all the possible number of neighbors, because this would mean you will waste a lot of compute on ghost nodes. But usually, in nearly all of the cases, the added benefit of having fixed arrays will always outweigh, these things. If you go to a really small system, again, this is, more delicate, but in general, this is the case. Okay, so we just simulated now 12.5 picoseconds. And if you want, you can run longer and play around a bit, but we will just continue with this for now. And we wanted to look at the dihedral angles. So we now sampled this peptide at a fixed temperature with normal MD, and wanted to see how much of this energy surface is getting explored. And if we run this, we have these two little plots here. On the y-axis, you have the dihedral angles for phi and psi, and the MD steps. And you can see, okay, they changed a bit, it wiggled around a bit, but nothing much changed. And you can especially see this in this other plot where the color is saying at which step we are. And then we have this, again, the different angles. And we can see that it just explored this little region here of the dihedral angles. And this is because the barrier is too high to be really well explored at this temperature. Of course, we can go to higher temperature, but this can only carry you up until a certain point, until your molecule, for example, breaks apart. And we will see in the next part how to use metadynamics for that. There's also some bonus here, so you can plot the Ramachandran plot, but of course it will just be this little dot here. And we will see later that we can cover much more. Okay, before I show you the command line interface, are there any questions so far with respect to JAX, JAX-md, or the code I just showed you? Okay, again, if you have questions, I know this is can be a bit overwhelming, or very new, you can just come to me and ask. So, as I promised you, this is all very, we created some wrappers in the Solar repository, which takes away the need for you to code this explicitly. If you do simple things like optimizing structures or running NVT, NPT dynamics, you can just use this command line interface. You can just use Solar and then have this opt function or keyword, and then you can define the input and output, the cutoff, the cycles we talked about, so the outer and inner loop, some threshold for the forces. And then you can also do dynamics too. So NVT, for example, but you can also do NPT. And then you just have to, again, define the settings, but you can just do this like this, and you don't have to code all these things I just showed you. But if you, of course, want to have some workflow, like, I don't know, relaxing some polymer structures, for example, and you have some different pressures and temperatures and so on, then you have to use some of the code I just showed you. I will show you how on the cluster how I use the command line interface. Again, I apologize, there was some issue with the Conda environment, but I can run it, of course. So here I defined what I just showed you, and can just run the optimization like this. And then I also have the NVT here that we can run once the optimization is done. So we can take a look at the output in a second. Yeah. Okay, before we move on to part 2, again, is there any questions? Okay. I will just wait until this will take a minute just to set up all the stuff, but running itself should be very quick. Okay, so in part 2, we'll now look at metadynamics with PySAGES. You can look at the Colab here. I also put it in the chat, but if you want, you can do this. And then maybe once you are in the Colab, I can show you the output of the command line interface. Oh, they are the same. Oh no. Okay, I'll just. Oops, it's a bit too big. Okay, I hope this works now.
Yeah, no,
Okay, great. Sorry for that. Yeah. And feel free to download the Colab. It's just a Jupyter notebook, so you can use the code. Okay. This is still running. Okay. So now, before we move on, we have the optimization with the command line interface. So this is how it looks like when you use the CLI. So it has some info on the settings. It will detect GPUs, for example, and then it will also basically print out the energies and forces and so on. And here you can see again, it first takes some time to compile it, but once it's compiled, it will be very quick. And again, if you go to a bigger system, so people in our group, yeah, see now this was very quick, and use it for simulating thousands of atoms, and there you can really see a difference with the compilation. And then once you, for example, have compiled it, you can also run the MD. And I will show you how that looks like once it's done. Okay, so everyone has the second notebook now. Great. So now we will use PySAGES for metadynamics. And PySAGES is just a package written in JAX that lets you do metadynamics. And for now, I will show you again how to do it with a custom code. But soon, with the release with Solid 2, I think there will be also a command line interface to run metadynamics through the Solr repository itself, and I will show you at the end how it looks like. But for now, you would have to use something like this. Okay, so again, we import some stuff. Now the new things are, well, again, you have to install the environment, right? And new things are the PySAGES functions and modules. So this is all from the first part. We define the structure. We optimize the structure, define the dihedrals and so on. And just print the dihedrals of the relaxed structure. So this is all just like part one. Now a bit of theory. I will give you the most important parts and intuition, but of course you can read through this in peace if you want. So the idea of metadynamics is that, as we saw, that if you run just an MD, the barriers can be too high. So we would have to run lots of, hundreds of nanoseconds maybe to sample, for example, the hedrals to some certain degree. So you would always be just stuck in some local minimum, and it would never escape, and we wouldn't explore the free energy surface, and which is called the rare event problem. So the crossing of the barrier from the initial state to some other place is a rare event, and in the timescales that we can do with normal MD, this is very rare. And in metadynamics, what we do is we define a collective variable, which is in our case our dihedral angles. So this is one caveat of metadynamics. You have to know what you're looking for. And then we place potentials along these collective variables. So if your dynamic has already visited a dihedral angle, it will place artificial potential there. It will push your system away from this already visited dihedral angle. And this looks like this. So we, in our case, we have some Gaussian potential. So we put this on every 1000 MD steps, the stride. So every 10 MD steps, we place a potential on this collective variable at this point. For example, the dihedral angle is 90, and now we put a potential there with some height and width that will push away the system from visiting 90 degrees again. And then with this potential, you can of course get the force, and this will push the system. And when you run MD, you will always add this biased force, and it will try to sample new regions. Now the problem is, of course, this is a bit artificial, and we want to have the real energy surface back at the end. But if we run this long enough, we can we have the free energy surface by just having the negative value of this bias potential that we created. And I will show you a little movie that will exemplify this. So this is standard metadynamics. Again, at certain MD steps, we just place a potential that pushes us away and lets the system explore more in a shorter time frame. We of course have to set the stride, we have to set the height of the potential and the width. But this is the price we have to pay, and of course we have to define the collective variables. One problem with normal metadynamics is that we always put the same potential at one place. So it will, even if we visited a place 10 times already just by chance, we'll always stack up these potentials with the same height. And then it's not really clear, it doesn't converge to a certain value, so we don't really know where to stop. And it also wastes time in regions that it already visited. And one idea is that we modify this potentials that we add at this point. So as a function of if we already place the potential there. So now if you can see here, when we create this potential, we have this this value omega that scales this this potential, and usually it's just a fixed value that we set at the beginning. And in well-tempered metadynamics, this is again the function of the bias potential in this place. So if there's a big potential already, because we added a bunch of potentials there, it will add a smaller one. And this has the benefit of like converging to a value, which we can see here. So we can run our dynamics, metadynamics, and we can observe if it converges, and then we know when to stop, for example. But again, we add another hyperparameter like this tau or the delta t, which comes into play here, where we define how we scale or how we scale the biases we add. So there's some info there on all the parameters we introduced, but the important point is really that, as you can see, when we don't do metadynamics, we'll always be stuck here in this little valley. When we do normal metadynamics, we can see how the bias is increasing and filling up. And you can see, if you look closely, that it will always at the same height at every place. And here, in well-tempered metadynamics, at places already put a large potential, it adds a smaller one. So, for example, on the sides, it doesn't add as big of a potential, but here in the middle, it adds bigger potentials. And this would just, go up and up and up. And here you would have some constant at some point. Okay. This is the theory. Again, we just put potentials to push our system away from regions that it already visited. And in PySAGE, there's a lot of convenience in the package so that we can easily run metadynamics. First convenience is that many collective variables that are typically used are already defined, like the dihedral angles we were looking at. There's also others. You can take a look at the documentation, for example, and see different angles, radius of duration, for example, distance metrics, and so on. But of course, you can also define your custom ones, but there's some pre-made. So now we again use our indices, which we also use for our custom function, and have a collection of collective variables. Now there are some technicalities how to put in this double neighbor list into PySAGE, but if you're interested, you can read through that. Otherwise, we have this code here where we generate some context for PySAGE, like how to initialize a state. In this case, we generate this JAX-md state that we already used in the previous part, but PySAGE has some backend for that. And then we create, again, a step function for PySAGE where we say, we define some way to update our current state, just as we did in the previous section. And yeah, at the end, it gives you a function that updates the state again. So this we will use in a second. Again, it's a bit technical, but if you're interested, you can read in there. And as I said, in the coming release, we will give you some glue code that will let you run this without defining it yourself. Then we have some settings for our metadynamics. As I said, there's a lot of parameters involved. We have the height of our potential, the width, the stride. So at every 200 step now, we will add a potential, number of Gaussians or potentials we will place maximally. then this delta T, which is used in well-tempered dynamics to scale the potential at one place, and just a grid for the collective variables that we later use for plotting and getting the bias potential. So here we create this grid I told you about. So we just go look at the different dihedral angles from -π to π. And here is what we're here for. It's the function that actually lets us run the metadynamics. So we give it the collective variables function, the heights, and the other settings. And then we can run. So first we have to, again, set some time steps. You can play around with these settings too. And yeah, some stuff like logging and log files. So this would place all the potentials that we place during the metadynamics, and this is the trajectory file that we have at the end. And then we just define some callback function that will let us plot some stuff, because in PySAGE you can define some functions that are called during the metadynamics, and this is just what we define here. So it will print again the degrees and the number of steps and so on. And then you combine everything. So we have the method, which was the metadynamics object or function that we defined. We have this context, so updating the states and some other variables, and then you can just run this. This will take a bit longer, but you can see here now that the elapsed time and now the angles that it visited. You can already see it's a bit more diverse already. And here it also tells you how many hills it already deposited. Yeah, now we just wait until this is done. Does anyone have questions about metadynamics or PySAGES? Okay. So we just wait until this is done, and then we can look again at the plots we knew from the first part and see if we explored more than with normal dynamics. And normally what you would do is not just run one trajectory, but you would run multiple, and then run as long as all these trajectories are converged to, so that they all in the end produce the same potential. But in this case, we only run one, and also not very long. But because despite using metadynamics, we still have to run longer than like the 12.5 picoseconds that we run here. And again, this is not very fast on here on my laptop, especially because this is a small system and we just use a normal loop here, but yeah. Yes, please.
So far, it's running faster than your laptop.
Yeah, but
So is it because the system is so small that GPU is just synchronized?
yeah, it's very small, and you use the T4 thing or something, right? Yeah, it's just because the system is so small that it doesn't fully utilize the GPU. And if you go to, I don't know, 1000 atoms and then you try running it with a CPU, and GPU will definitely see a dramatic speed up. Okay, now it's finished. We can save the trajectory, but no, it's not that important. Now we can plot this again, and we can see that it visited much more than before. So if we put these next to each other, it's a bit small, but you can see we just visited a small region with normal MD, and with metadynamics we sampled quite a few different degrees of these dihedral angles. And this is not just about dihedral angles. You can think of reaction coordinates, for example, or if you're folding a protein, you can use the root mean square distance between your initial state and the one you're simulating, also as a collective variable. So, yeah. And then we can look at the Ramachandran plot again. Now I filled out the non-visited region with yellow, so high energies, but you can see that, you know, we visited this part. It moved over here and there. So, and here you can maybe even see that it's transitioning from one basin to the other, which you couldn't see before. And a colleague of mine, Evgeny, was kind enough to run this to completion basically for one trajectory. And then it looks something like this. So it really, so these are minimas, relative minimas of the molecule, and then you have these transition states between these minima that were all visited using metadynamics, and you ran this for, I think, 4 nanoseconds or something. Yeah. Any questions on this? Yes.
How do you determine which states exactly
I mean, when you have, he did some other stuff I didn't show you, but for example, a transition state is when you if you look at the Hessian, for example, you will see that it has one imaginary frequency, or one frequency that if you move the structure along this this frequency, basically, it will go down in energy because it's on a saddle point. So, for example, if you have a reaction, or like a transition state of a SN2 reaction, if you're a chemist, you maybe know it, then you can see that if you move along, like if you push the center towards one of the attacking atoms, it will go down in energy, or the other way. So that's how you can spot transition states. And this is a well-studied system. So you can, there's a lot of work done, and there's tables of all these transition states and so on. Okay, and before I finish, I want to have this slide as a little, just as an overview where you can get all these things. So of course, solar, you have the main repository where you have the pre-trained model, and it has the command line interface I showed you. We also have an implementation in PyTorch. So if you didn't get warm with JAX, or you want to do some prototyping, for example, you can use this repository. It has a bunch of more features, more geared towards, you know, training models and fine-tuning, but it also has a connection to LAMPs, and also lets you transfer weights. Like if you train a model in Torch, you can transfer the weights to JAX and then use JAX code. For example, if things are not fast enough for you, you have you're more familiar with PyTorch and like the code more, then you can prototype in there. And then we have, yeah, the SAGES repository, and also the JAX-md repository. And it's also, there's more support now, so there's more development now. And if you, for example, find mistakes or issues or want features, we're actively developing this again. And there's some more features I didn't show there. Okay, that would be it for the first part of the hands-on session. Feel free to play around more with the code. If you have more questions about Solr, maybe the PyTorch code, which I wrote, so I will gladly help you there. Or in general of the things I showed you, you can just come to me. And Florian, do we take a like a break before moving on? Yeah.